It's a big crowd, guys.
Where's our students?
They're over there.
No, just one, two.
Where is your
Where's your boyfriend? Sleeping?
Really? Okay.
No, he had to go to trip.
Good afternoon, everybody. I'm going to start a little bit earlier today because this is just a half an hour talk. It's a special talk. Before I get to that, I would like to make just a reminder that we continue the seminar series next Friday with a 1 hour talk. That will be Alan Aspurukazik, who is going to be talking about billions and billions and billions of molecules in the universe. Following that is on 27th of March. I just want to make sure everybody knows that that seminar is not going to happen here, but at the Science Center, room E. So we'll put announcements, but just since you're here, I want to remind you. So next talk is next Friday, and then the following one is 2 weeks from that on the 27th. So today we have a little bit special seminar. It is, I don't know how many years we've been running this seminar series, but this is the first time we have students talking. And as Ross put it, about time. We have the opportunity for the students to give their perspective of the work they're doing. And this is a particular program that is, personally involved. This is one of our, and only for now, international collaboration with the University of Chile and other institutions in Chile. We have this exchange, or we call it Innovative Learning Exchange. If you look at the title, it actually makes the word Chile. So it's an infinite loop if you think about it, because Chile is in the Chile, and you can go in and out. Okay. Anyways, enough of that geeky jokes. So my pleasure to introduce our speakers today. In this program, we have 5 students from Harvard. Lila Faiden is been sick. She's not feeling very well since yesterday. I checked, and she's telling the truth, and she's not just escaping. Also, Min-Jae Kim, who is over there from the Applied Math Department. We have 2 students from IACS, Sabrina and Diana, and finally Chu Fei from the Statistics Department. So the talk is only for half an hour. They're going to tell us what they have done in Chile, what they have learned, and I should not take more of their time.
Mic is okay? Check. Okay. So I'm going to introduce a little bit about this Chile-Harvard Innovative Learning Exchange Program, which is hosted jointly by IACS here from Harvard, as well as from the Center for Mathematical Modeling from University of Chile. So in general, this program runs for 5 weeks, 2 weeks preparation here in Cambridge. We were doing some literature review, discussion of the problem, and some idea generation. And then 2 weeks in Chile actually working on the problem, with 1 last week finalizing reports, presentation, and posters. And this program takes place in January every year. So for the participants, most of the students from the Harvard side are from IACS, such as myself, Diana, and Lila, who unfortunately is sick today. And then we have Xufei from the statistics, and then we have Min-Jae from applied math. The other side from Chile, we had students from University of Chile and Catholic University of Chile. And then, of course, we had wonderful staff and faculty from both Harvard and the Chile side. Okay, so we actually went to Chile. So if you see, that's how we went. So the first week, we spent our first week in La Serena, which is in the northern part of Chile. We worked together with researchers and scientists from the Gemini Observatory and Cerro Tololo Observatory, which we actually went to visit. And then the second week, we went to Santiago, which is the capital. And over there, we were working in the University of Chile with all the students and the faculty as well. So basically, what do? We were given these 4 terabytes of data, consists of pictures taken by the Blanco telescope from Cerro Tololo Observatory. And our objective was just to identify everything inside of the data. If you look on the right, that's a picture of the Blanco telescope by itself, and that's actually where our data came from. And the picture in the middle actually is the picture of the Cerro Observatory. It consists actually more than just one telescope. It's like a bunch of little mushrooms over there. And the picture on the left is actually taken from inside of the Blanco telescope. And if you look, okay, let me try the pointer. So there is the primary mirror of the telescope, and then inside of this thing, there is a secondary mirror. So basically, when the light shoots in, it shoots onto the primary mirror first, and then gets reflected to the secondary mirror, and then reflected back all the way to something behind the primary mirror, and that becomes our data. Just to give you an idea of how our data really looks like, this is like a fancier visualization of our data. It's actually a picture taken by the Hubble. So if you look over there, there are various this swirl shape and fuzzy edge kind of thing. That's a galaxy. And then if you look at those like clear, like one single dot, that's like a star. So basically our job was to identify all of those from our data. And we had like almost like 500,000 of all of those pictures and something like that. So the learning objectives of this program is to work with open-ended questions, to handle real data that contains errors and artifacts and missing values, to formulate and implement computational methodologies, and of course to collaborate with various people from different backgrounds and culture. And last but not least, and to experience Chile, and we did. So we broke down our problem into 3 different parts for 3 teams. The first team is to do the source detection, and the second team to identify moving objects, and the third team to do classification. I'm going to move this speaker to my fellows to talk more in details about each part of them.
Is the mic open? Okay. Since Lila is unfortunately sick, I will take her part and try my best to introduce the tasks and goals for Team 1. So the main goal in Team 1 was to detect source and identification. So on the right, we see a couple of pictures of the examples that they got raw data off from the telescope. So first of all, they have to identify objects on those images. And the data were taken for 40 fields of the sky and were observed for 4 nights. So the telescope will take a picture of one field and move 3 degrees and take the next and then take the next. And each field is observed 4 times per night. So that gives us 16 epochs per field in the sky. And we were given about 20,000 images and 4.4 terabytes in FIS format, which is the astronomical format for storing images. So there were mainly 4 things that Group 1 performed. First, they have to remove cosmic rays. And cosmic rays are these little blue strikes that you see in the picture. And then after that, they have to identify, in this picture, you can see, I don't know if you can see it clearly, there are little circles around objects. So they have to identify objects from the background and noise. And then, so after that, they can extract features, for example, the time that this object was taken, the magnitude of its brightness, and error from the telescope, and such features like that from the objects. And then they generate catalogs for Team 2 and Team 3 to use to further identify and classify the objects. And last, they cross-matched what they have identified with the world existing observatory catalogs to see if there are any matches between our data and the existing catalogs. So this is how they removed cosmic rays. Cosmic rays are just very high energy charged particles that strikes the Earth in almost light speed. So because of this characteristic, they have very hard edges, and that's the main point in their algorithm of detecting cosmic rays. So they'll only have to detect the hard edges, so the algorithm was able to identify any size or shapes of cosmic rays. And so after they identify the cosmic rays, they'll have to remove it from the picture and then identify objects. So this is a picture of a 1D image of the 2D pixels of an image, and the histogram we'll see are number of photons counted in each pixel. So the sky has this background and noises. So this line right here is the mean of the background. So they have a 1.5 standard deviation threshold. So they count how many consecutive photons are above that threshold. And if there are about 5 or 6 photons consecutively above that threshold, then they can say there's an object there. So that's the first of all step of identifying an object. However, we see there might be like 2 things next to each other or even overlapping objects in the image. So they have to deal with that. To deal with consecutive, we see on the first picture right here, if you just identify consecutive photons above the threshold, you might get 2 things that are right next to each other. So how to separate them? You have to define a shape for the either stars or galaxies, and use the shape to sort of cut out the object, using either a circle or the shape of a galaxy to separate consecutive or overlapping objects. And so on the bottom here, you just see a couple of different methods of trying to identify different shapes of objects. And after that, Team 1 did a cross-reference with all existing Virtue Observatory catalogs, because we have limited information off of our telescope. However, if we do found cross-match, say we observed an object that also existed in other Virtue Observatory catalogs, we can get a little bit more information out of that, such as measurements of different color filters. And those filters can be very useful for us, Team 3, when we try to classify the objects. And then, so Team 1 was the team that dealt with raw data with the 4.4 terabytes of images. So we were given clusters at the University of Chile, and we were using 128 nodes and over 2,000 cores. Team 1 mainly, they did parallel and distributed computing on the cluster to identify objects off of those images. And so what they had was a catalog that contains the objects that's detected, their magnitude, their time, and whatever other features that was extracted. So Team 1 passed that catalog to Team 2, and Team 2 can do further analysis on the catalog. And now I'll hand it over to Shufei.
Hi, I come from Team 2. On Team 2, we have 4 people. We have Josefina, Pablo, Lucas, and me. We had a lot of interesting events in Chile, like the horse riding, the snail racing, and also we discussed a lot for our project. So this is our task for the Team 2. We need to do a lot of the classification based on the results from Team 1. Team 1 gave us a lot of the objects, but they could be the non-moving objects, they could be the moving objects. Non-moving objects could be the stars, galaxies, or some artifacts like the arrows of the observations, and some cosmic rays maybe left by the first group. And the moving objects, they could be the asteroids or some of the observations that happen to stay in a line. We need to detect all of them together. So the main task of our team is to do classification. Now let me introduce the classification between the moving objects and non-moving objects. Because we have 16 epochs of the same field, they are taken in 4 days, and each day we taken the observation 4 times. If we overlap them together, the non-moving objects, they could stay on a similar place. So there will be a repetition of that position. So we overlap the images and find the clusters in the images. We use the DECam, which is a very famous and useful machine learning method to do the classification. The advantage of DB-scan is that we don't need to know how many clusters we are looking for. So we don't know how many non-moving objects are there in the images. We could find around 500 non-moving objects from an image. This picture is an example of a field we get. You can see different colors in the picture. Different colors represent different non-moving objects. And you can see from here, we could find two little clusters. One is composed of 6 observations. The other is composed of 3 observations. We think this might be an example of the non-moving objects because after different observations, they are very near each other. And then after we get the non-moving objects, what's left is the moving objects. We'll classify the non-moving objects to stars, galaxies, and other artifacts. So to classify the non-moving objects, we still use the machine learning. Here is the flowchart of our team. We have the non-moving objects, and the non-moving objects, we have a lot of features from this. This also comes from team 1. In fact, they could generate 400 features for us, but we select 25 of them to classify the difference between star and galaxy, like the ellipticity of the object, like the magnitude, and something else. And also, there is an important feature called star-galaxy. You can see here. This is how the team 1 used the algorithm to calculate the probability this object could be a star. If this value is very near to 1, this object is highly possible being a star. If it's very near to 0, it's highly possible being a galaxy. Because we want to do machine learning, but we don't have any training set yet, we will use based on this value to build a training set. That is, if this value is greater than 0.9, we believe this is a star and label it. If it's less than 0.1, we believe this is a galaxy and label it as galaxy. Based on this training set, we do our algorithm inside this training set, and we could get an accuracy rate as 95%, which means our algorithm is reliable. And then we classify the testing set with the same supervised learning method and get some of the stars, some of the galaxies, and some of the undetermined ones. These undetermined ones may be because the image is too faint, or this images is some cosmic rays left by the first group. And we went to our astronomers to relabel these classes. They look at the images and label some of the objects maybe we don't detect by the algorithm, but they label it, and then we enlarge our training set. The training set is enlarged, and then we can do the classification again. In this loop, like we do this again and again, it's called the active learning, that you are learning based on what you have learned. After we finish the classification, we will give the stars to team 3, and team 3 can do further analysis based on the light curves or the other information of the star. Here is an example of our classification. You can see the left one is an example of the star. The star is always round, and especially the energy is always centered in the circle. But the difference is the galaxy. The galaxy is always elliptical, but some galaxies could also be round. But the energy distribution is a little different. The energy is more centered for a galaxy. And here is something that we couldn't classify. It looks like maybe a star, maybe a very faint galaxy, or even some errors because of the background noise. And then we are going to classify the moving objects. Some of the moving objects could be asteroid. This asteroid will happen in different epochs, but the position will change day by day. Some might be some observation noise that may be also, they happens day by day, but sometimes, most of the time, they don't make into a straight line. So we developed a new method to discover asteroid, and we found some new asteroids. We use this based on the Hopf transformation. Hopf transformation is a very useful tool to find the straight lines in images. Actually, we have two positions from different epochs, they can make to a straight line, and we can make all of the pairs together, and we compare which of the straight lines, they look very similar. If there is a lot of, maybe some straight lines, they look very similar, we can say maybe these points, they come from the same asteroid, and they can form a new discovery. But so Hopf transformation is a way to transform the feature of the straight line. And if these features, they are very close to each other, or in other words, they change to a cluster, we will classify them as an asteroid. So we still use the DB-scan to do the cluster, to find the cluster. Oh yeah, these are two examples of the asteroid we could find from the images. We can see that because they are taken in different days, some of the observations are very close to each other. They are in the same day, and after another day, because we have the daytime, and there is another 3 observations. This is an animation of the asteroid. Maybe you can see there is a very little red, blue, green dot here, moving around here. I hope you can see this. You can find that some of the non-moving objects, they look very different in different epochs. It might come from the observation conditions, but this moving object is very obvious that it goes from time to time. I will move on to the next group.
So team 3 is the students from Harvard. It's me and Sabrina. So for us, our goal is to classify what team 1 and team 2 has already identified. So we received, so team 1 created a catalog of all of the objects that they have identified off of the image, and team 2 classified them first into stars and galaxies and undetermined. We're only interested in the stars, and particularly only the stellar objects. So first we extracted light curves from the non-moving stellar objects. Well, light curve is the way astronomers represent a star, an object. And this is a simple example of one light curve from our data. On the x-axis, it's time, and on the y-axis, it's the magnitude of the brightness of this object. And then, so we're only interested in non-moving stellar objects, and they are sources that will change their observable luminosity. So below, you see a picture of, this is an example of a variable star. Variable star is a kind of non-moving stellar objects. So these stars, their brightness change in time. So this is one of the most important features that we use to identify and classify these objects. So as the star gets bigger, it will be brighter, and when it's smaller, it's less bright. So, and then the second goal of the team was to extract features that will be using those features in using machine learning algorithms to classify. So there are many features that you can extract from an object. Simple features could be just the mean of its magnitude or standard deviations, and some of more complex time series characteristics, such as autocorrelation functions. And so using the light curves, we can extract features. And this is an example of some of the feature distribution of some of the features from an existing world database, because we do need some training set from the existing database, and then we'll train these and fit them on our test data. And after feature extraction, we had almost 500,000 light curves, so we extracted features from all those 500,000 light curves, and then we need to classify the variables and non-variable objects, and first to these kinds, and then further down into their subclasses. So these are so for a stellar object, it could be classified into many different classes. First is variables and non-variables. So for variables, as I said, they're stars that will change their brightness across time. There are periodic ones and non-periodic ones. And example of periodic ones could be ellipsing binary stars and pulsating stars, and non-periodic ones include quasi-stellar objects and supernovae. So for non-variables, they're just objects whose variability cannot be detected, so we'll only classify them as non-variables. First, we used unsupervised learning to just take a brief look at the data and see if there might be any observable trends just in the principal components. However, we couldn't see anything. This is the data is all clustered when we just use unsupervised clustering methods. So then we use something called transfer learning. So transfer learning is on this left. This is traditional machine learning. And in traditional machine learning, you have a training set and a data set. And the underlying assumption is that your training set and testing set came from the same feature space, and all the features are they're uniformly distributed so they should have same features extracted in the same way. However, this is not our case because we do not have any testing data from this particular telescope with this particular setting that we can use as our training set. So what we need to do is transfer what we know about these objects to apply to what we have in our data. So in order to use transfer learning, first we have to make sure that our testing set and training set are in the same feature space, and this is how we did it. So I mentioned that Team 1 helped us cross-match with existing world catalogs. Astronomers, they'll define the sky into fields, and they name these different fields, and they'll continuously observe this field. And one of the largest fields is called supercosmos, and this is the field where we found the most cross-match. So we found over 600 cross-match objects in our database and the supercosmos field. So we used those 600 objects as our training sets. And then now that they're in the same feature space, we have to make sure that the features will have a similar distribution. So in order to do that, we first trained a random forest classifier on the training set. So here is the picture of before transformation, after transformation. So we had to transform. We have a lot more data than we do in the testing set than we in the training set. So what we did was we normalized both distributions so that they'll share similar means, and then we trained a random forest classifier on the normalized features. And then using this method, we were successful in classifying these objects. And this is the classification result. So since we have a lot of data, so on the left here is just all of the data that we have after classification, and we see that we can already see some pretty identifiable classes. And on the right here, I just plotted a couple examples where we can distinguish between the different kinds of stars. And then, so after we have classified these objects, we'll pass them back to the astronomers so that they can further study these objects in the future.
Okay, so what did we learn? This entire problem, there was not exact solution, and the data that we were given was very messy with a lot of missing values and errors and artifacts. All of us, students from astronomy, students from computer science, students from statistics, all of us had to work together very closely to figure out a way around it. And we utilized high-performance computing and techniques from machine learning, such as active learning, to help us tackle the problem. And we did experience Chile very much. So the last is a link to the webpage of our work if you want more information about it. Last, we just want to say we thank all the wonderful staff and faculty members from both Harvard and Chile that helped make this program possible, and we all enjoyed our experience. So thank you all for coming.
So we have time for questions.
Yes?
Love to hear questions.
Just curious a little bit on the implementation details. So what languages do you use for the feature identification and then the machine learning and some of those other?
So for feature extraction, I think Team 1 was mainly using something called X extractor. I'm not exactly sure what language it was in because I didn't work in the team, but for Team it's in C. And then for Team 3, we used Python mainly for all machine learning algorithms.
And for Team 2, we also use Python.
So, I mean, did you really need a HPC? I mean, do you really need a cluster? I mean, if you could have written a faster CI algorithm. It's only 4 terabytes of data. It's one hard drive. Couldn't you have just done it on like a workstation?
I think it's really
It would
from.
have taken 200 days.
And also, since our teams were like consecutive, so we sort of had to wait for team 1 to finish and then we can continue. So we didn't have, although we were there for 2 weeks, but we didn't have the entire 2 weeks to work on.
The team 1, this program that I received, not the most optimized work. It took 2 days to analyze the program. And that's on 1,200 codes.
Yeah, but I'm just saying that when you're spending most of your time moving the data over the network.
No, it's just a lot of computation.
Yes.
This is completely from a different angle of question, but in terms of maybe introducing these skills and what you're doing to a younger set of scientists coming up, for instance, in Chile, I wonder if there could be anything that could be added to the program where you might do a little bit of a presentation to high schools or something like that. That would be
They
like
would love to.
Huh? I'm involved with STEM
I volunteer
education.
them.
I'm involved with global education and STEM education. I have a lot of different layers to my work, but I'm wondering, it would maybe take another few days. I don't know if you would have access to stay a few more days, but it would be a really cool add-on.
You mean to do presentation in Chile to the group?
Yeah, to connect with the school.
Well,
It's
it's not, I mean, I like the idea. It looks like they have more fun, but there's a lot
no,
of
it's
things to be
intense.
done. It's
Oh,
very
like,
intense.
yes. Just a thought.
I think what you did is really cool, and especially as you come up with some variables and ask for other neat things. Part of the program that you were working in has titled Dark Energy Survey. And I'm just wondering, did you learn anything about dark energy?
I learned the picture that I showed, the fancy visualization of the Hubble picture that I showed, that is, if you saw the ring, I think that was like because there was a dark matter in the back of it, and that sort of like made that ring shape, which is close. The Einstein ring shape showing there, right? That's what you're talking about, the picture, right? And that's all I know.
You didn't identify dark energy.
I wish I did.
That's next year's program?
Yeah, that's a goal for next step.
Okay.
Yes.
So in terms of what the astronomers care about, do they care about once you pass part 3, the pilot, are they interested in statistical, for example, the number of stars you have, different types, or is it more than a certain perspective?
I can talk from So one is, I think it's a large part of the sky. You get inferences about population. Yeah. So the first thing is to get inference about population because it's a big part of the sky. Second is that we haven't looked at the data very carefully, but there are certain classes that are very rare. So there may be only 10, 20 objects in the sky identified. So we want to look into that. And what was the other question, Chris? I forgot.
I think that was it, just about whether
No, then there is also, because again it's a large, there's 500,000 objects. If we do find a class, then we can do a post-mortem analysis of the features. What are the periods? What are the things?
So you mentioned in part 3 or part 2 about doing PCA. So presumably you have to have a big data set, like a number of for each to do PCA you must have had like for each object you have like probably a big vector associated with it. So I just wondering if you could talk a bit about what you do PCA on.
I think we just did on the entire data set of all the light curves we were given. It was, do you remember how big it was?
It was the
It was on
the features. There were about 30 or 40 available features, but since our data, we only had 16 epochs, it was only for 4 days. So some of the features cannot be extracted just based on these data. So I think in the end, we used about 15 of those features, and we did PC on those extracted features. And originally, we thought if the features are distinct enough, we might be able to just see something off of clustering, but we didn't. So then I think after that, we didn't use PC anymore for further classification.
Yes.
I heard about a trans-Neptunian object. Could you elaborate on that?
I'm sorry, what was that?
The show the asteroid, the one with the animation.
Okay, the animation one.
Oh, that's it.
Find it. This one?
That's it. It's a new one.
Yeah, we went to other websites to find the positions, the time, if there is asteroid appear them, and we think that we couldn't find it. But we can't say that it's 100% sure an asteroid, but we think nobody has found it before. Yeah, and they move in a straight line. We compare their magnitude and the shape. Yeah, we think that it's a new asteroid.
You can name it after that.
What was the biggest bottleneck in processing?
I guess it differs group by group. I think for group 1, it was mainly computation power because they did take them after everything was done, all the algorithms were written. It literally took a couple days for them to just waiting and run an algorithm, and we can't do anything in between since we don't have the results. For us, it was mainly trying to see which features are the most important ones that can distinguish between the different classes. And for Team 2?
Yeah, and for Team 2, actually we have the classification tasks. So I think the bottleneck is to how do you find the classes more efficiently, and we are waiting data from the first group, and we will give the data to the third group. So I think we also need some computation speed because we are in the middle of this task, so we need some computation speed, and we are sometimes waiting for the first group, and we need some interaction between the two groups.
Other questions?
Thank you.